Good evening, everyone, and welcome. Thank you for being here with us tonight. Tonight, we have the pleasure of exploring one of the most exciting intersections in modern science, the role of artificial intelligence in material design, with Professor Sir Konstantin Novoselov. But before we begin, I wanted to spend a few words regarding the project behind this. I'm Valeria Morra, and I'm leading the initiative of the Institute for Advanced Studies, and it was developed in collaboration between Fondazione Compagnia di San Paolo and the Italian Institute of Artificial Intelligence. Our mission is to bring together scientific excellence to explore the frontiers of knowledge and innovation. We focus on connecting research, engineering, and real-world impact. With that in mind, it is my pleasure to invite our institutional representative to open the evening, Alberto Fossi, General Secretary of the Fondazione Compagnia di San Paolo, and right after, Professor Pammolli, President of the Italian Institute of Artificial Intelligence. Thank you.
Thank you. It's a great pleasure for me to bring the greetings of Fondazione Compagnia di San Paolo today, since moments like this remind us how fundamental discoveries in science, like those that Professor Novoselov brought to the Nobel Prize in Physics, continue to shape entirely new technological and scientific revolution. I would like to thank the AI for Industry Foundation and the Compagnia di San Paolo Institute for Advanced Studies for organizing this event and for creating opportunities like this for our industrial and scientific community to engage with some of the most influential researchers of our time. We are particularly honored to welcome Professor Novoselov. His groundbreaking work on graphene and two-dimensional materials has not only transformed the field of material science, but has also opened entirely new possibilities for technology and innovation. Our foundation, Compagnia di San Paolo, fostered the birth and supports the Compagnia di San Paolo Institute for Advanced Studies at AI for Industries, with three goals in mind. First, to boost the international dimension of this institution by connecting it with leading scientists from around the world. Second, to enhance the visibility and positioning of AI for industry within the global research landscape. And third, to bring here the leaders of the scientific and technological transformations of our time, so that their ideas, their discoveries can inspire researchers, students, and the broader community. Today's lecture perfectly embodies this vision. We are entering a fascinating phase of science discovery in which artificial intelligence is becoming a powerful partner of fundamental science, from physics to chemistry to material science. AI is allowing researchers to explore vast spaces of possibilities, to discover new materials, and to design structures with properties that are once almost impossible to imagine. In fields such as materials, AI is accelerating the discovery of new structures and enabling scientists to explore possibilities that were previously beyond reach. I just mentioned neuromorphic computing. Fostering this dialogue between AI, fundamental science, and the international research community is precisely the spirit in which we support initiatives like this. With this spirit, I wish you all an inspiring lecture. Thank you very much.
So it's a great pleasure to have Professor Sir Konstantin Novoselov, Kostya, who's also a friend, and I really thank you for being here today. Kostya studied at the MIPT, at the Moscow Institute of Physics and Technology, and then completed his PhD in the Netherlands, in Nijmegen, and then in 2004 at the University of Manchester, he co-isolated graphene, and one-atom thick material with exceptional properties. For this discovery, he was awarded the Nobel Prize in Physics in 2010 for for groundbreaking experiments regarding the two-dimensional material graphene. His research focuses on condensed matter physics, particularly two-dimensional materials, their heterostructures, and more recently the use of artificial intelligence in material design for functional intelligent materials. He's currently the director of the Institute of Functional Intelligent Materials and Tan Chin Tuan Centennial Professor at the National University of Singapore, and he's also serving as a Professor of Physics and Royal Society Research Professor at the University of Manchester. He's also serving as the President of Constructor University in Germany. I will come back then to a short description of the lecture that Kostya will give today, and the reason why we thought that to have his experimentally driven approach to the role of AI for new materials and for the discovery of new materials on the one side, and then the role of new materials for AI will have been a unique opportunity for our researchers, for the community to interact with him. Then I want to mention the fact that the Minister of Industrial Development, of Industry and Enterprises and Made in Italy sent a message, so I really thank the Minister Adolfo Urso for this. I will read it in Italian, Kostya has the English translation for that. Ringrazio il professor Pammolli per l'invito e rivolgo un cordiale saluto ai partecipanti alla Lectio Magistralis AI for Material Design, promossa dall'Italian Institute of Artificial Intelligence for Industry e dalla Compagnia di San Paolo Institute for Advanced Study. Nel vostro evento date voce a un'eccellenza della ricerca internazionale, il professor Sir Konstantin Novoselov, premio Nobel per la fisica, che offre un contributo fondamentale per comprendere come l'intelligenza artificiale stia rivoluzionando la scoperta e la progettazione dei materiali. Le potenzialità di materiali autoriparanti, dotati di memoria e capacità di adattamento, così come lo sviluppo di nuovi materiali per architetture computazionali alternative, rappresentano opportunità strategiche per aumentare l'efficienza energetica e la sostenibilità delle nostre infrastrutture digitali. L'iniziativa conferma il ruolo centrale di Torino come polo dell'innovazione. L'istituto, fondato dal governo a maggio del 2024 e con sede all'OGR Tech Hub, è molto più di un centro di ricerca. Con un approccio integrato tra ricerca applicata, sviluppo tecnologico e innovazione industriale, AI for Industry si concentra su settori chiave, manifattura, automotive, aerospazio, e investe sulla formazione attraverso la sua Academy, contribuendo a costituire competenze immediate e strategiche per il sistema produttivo nazionale. Coinvolgete grandi imprese che hanno fatto la storia dell'industria italiana, come Stellantis. Siete un polo di attrazione grazie alle competenze che sapete concentrare e valorizzare a supporto dell'innovazione dei processi, così da diffondere progresso e crescita. L'evento si inserisce in un ecosistema nazionale per l'intelligenza artificiale sempre più maturo, sostenuto da una normativa nazionale dedicata, da politiche per i data center e da investimenti nel calcolo quantistico. Il tutto orientato a promuovere lo sviluppo tecnologico in un quadro regolatorio con un chiaro approccio antropocentrico. Concludo applaudendo alla vostra iniziativa e sono certo che l'intervento di Sir Konstantin Novoselov rappresenti un'occasione unica per coniugare eccellenza scientifica e impatto applicativo, orientando ricerca, industria e politiche verso un'innovazione sostenibile e competitiva nel campo dei materiali e dell'intelligenza artificiale in Italia. Grazie Adolfo Urso. Quindi ringraziamo il Ministro, and then I will switch to the lecture of Kostya, of Sir Konstantin Novoselov. A number of challenges of the modern world could potentially be resolved at the low level, at the lowest level, on the low level with innovative materials. However, new types of materials need to be designed for such applications with some characteristics and features of biological systems. Those with self-healing capabilities, with memory functions, those which can evolve differently depending on external conditions, and adapting to external conditions. Professor Novoselov will be discussing the methodologies to design such artificial living systems and the areas of their application. At the same time, since AI is playing a crucial role in the process, he will discuss a variety of AI approaches for materials design. We had an interesting seminar here a few weeks ago on the role of AI for science, and this is going to be a concrete example of how AI is somehow shaping and affecting and reshaping also the experimental work and the interplay between experiments and simulations and theory building. Then, finally, Professor Novoselov will consider the utilization of new materials for novel beyond von Neumann computational solutions, so exploring the other side of the interaction, which allows significant reduction on the power consumption of modern data centers. So, Kostya, really thank you for being here today, and the floor is yours.
Afternoon, everyone. Can't see anyone in the audience. And it's really a great pleasure to be here. Hamid, thank you so much for this invitation. So we know each other for donkey years, and so Fabio is a good friend. Even worse, I follow his footsteps, and so might end up in Turin at some moment as well. Hopefully following your footsteps would save me from my usual habit to get into troubles, but we will see. So the title for today's talk is Material for the Future. I understand it's a very, very pretentious title. Let's see if we can survive up to it. But still, it's nice to start with graphene, because it's really it's one of the simplest possible materials. It's only carbon. Carbon is one of the lightest elements, only 6 electrons, 4 valence electrons arranged in a simple honeycomb lattice on a plane. Really, nothing could be simpler than that, and yet it has a number of superlatives. So it's been one of the most conductive, thermally conductive, impermeable, stretchable, strongest, flexible, transparent, and so on, and so on, and so on, and so on. And what is really interesting, especially for physicists, is that all of those properties are really coming from the symmetry of this crystal. So that's really very special for any physicist. So that just looking at the honeycomb structure, knowing its symmetry, you already know quite a lot about this material. So I won't go much into details into physics. I'll leave all the challenges for you guys until later. Just let me give you show some of the maybe unusual things which we see in this material. I'll put it just as a simple cartoon. So from your hopefully not everyday experience, you know that if you run your classical car into a wall, you would of course crash it, right? It's just some of us unfortunately experience this. Now in physics there is a phenomenon called quantum tunneling, and if you've got a quantum car, which is a bit difficult to get, but Tesla only produces a few of those. But if you've got a quantum car, there is a finite, small but finite probability to go through this barrier, so without crushing. So with cars, very, very rare event. I've never seen one, but say with electrons, we see it every day, and that's actually one of the reasons why we have this problem with the power wall, why our processors overheating all the time. So quantum tunneling plays quite a big role in that. But still, usually it's a really small effect to go through the wall. Now, if you would have electrons like we have those in graphene with the properties like electrons in graphene, the probability to go through the wall is 100%. And that's something which we measure in our devices every day, and that's the reason why graphene has a lot of potential for electronic applications and many other applications. However, before I go to promise you some future applications. Let me show you what graphene has done for us already. Well, one thing it's created workplaces. So many of my former students opened multiple companies, and some successful, some less successful. And it was meant as a joke until one day I received my regular copy of Glamour magazine, and then I'm not sure if you can see it, but so it's what is written there: 5 jobs our kids will be doing, and there is virtual architect, avatar stylist, active makeup developer, and graphene engineer. So, and who am I to argue with Glamour, right? It's, it also provides entertainment. I know it's quite an old sitcom, but I'm sure some people would still remember the Big Bang Theory, and so it's basically a sitcom about four friends in Caltech, and the main protagonist, Sheldon, is in one of the episodes, he's trying to figure out why electrons in graphene behave as massless quasi-relativistic particles, and he basically spends the whole episode trying to deliberate on it. You all know this is because of the honeycomb symmetry. He really struggles because some of the formulas on that whiteboard are actually wrong. And it also gives shelter. So if you fancy to ever live in Tallahassee, Florida, you can quite as well live on the graphene lane. But in reality, there are indeed quite a few really opportunities, and quite a few of those have been realized already, from electronics and optoelectronics to composite materials, energy sensors, and so on. And of course, for many of us who've been working with graphene for years, it's quite a special material because many new phenomena have been discovered. When it comes to application, it turned out that it's not that special anymore. So it followed exactly the footsteps of all the other advanced materials before it. So before it, there were fullerenes and carbon fiber and carbon nanotube. And usually the first application which you see with those advanced materials are the composite materials, usually in the spot goods, because those companies, they like to charge you a huge premium for just tiny improvements of the properties. I should say that we are guilty as well. We collaborated with Richard Miller and McLaren to create the world's lightest, but also world's most expensive watch. It's 1 million Swiss franc for 32 grams of watching, so definitely by far most expensive per gram, if you can do, if you buy watches per gram. But then it became more real, and so these days, many automotive companies, they would use graphene in their cars for various reasons. So this is BAC Mono, so they use it because they want the lightest and the strongest. But in many cars, it would be used for conductivity, as noise canceling materials, and so on and so on and so on. If you go to China, pretty much every single phone, every single Chinese phone would use graphene either for batteries or for thermal management or for both. So this is basically a must now in that part of the world. And if we need to think about the future, so I would say, so Europe is now very actively investing in optoelectronics, in optical interconnects, and graphene must play, so they're actually building those fabs where graphene is integrated into the silicon photonics, because all the traffic, all the internet traffic which we use goes through the optical fiber. So as photons, unfortunately, we don't know how to deal with photons. Every time you want to do something with your optical signal, to multiplex, to modulate, you have to convert it into electronic domain, use the usual transistors to modulate the signal, then convert back into photons, send it through the fiber. Ideally, you don't want to do this. You want to modulate the signal by itself, but for that, the optical signal, but then you need materials which can change their optical properties by applying voltage, and that's all graphene. So it's being now developed into at least 3 optoelectronic fabs across Europe. Okay, I'll probably skip it maybe for experts in the field. For years, the loss of quantum phenomena in materials have been studied in gallium arsenide type of materials in 3-5s. Because you get very, very high quality. Quality is measured in terms of mobility. It's how fast your electrons move. So silicon in your transistors usually 1,000. So in those materials which are suitable, which we use for quantum computing or quantum measurements, the mobility is 50 million. And graphene, within a short period of time, we already managed to overcome that limit. So it's really one of the most quantum welcome materials which we've got these days. So, of course, when we talk about applications, we need to realize that the properties are great, but we also need to know how to produce this material, because a long time ago we started with a very simple way how to make this material. To make graphene, you use basically Scotch tape. You take graphite. Graphite is the material which you find in your pencil, and it's a layered material, so it's easy to split it into thin flakes by shear forces. You just when you rub your graphitic pencil against paper, you basically just sheds those flakes from the layered material graphite. And we simply used Scotch tape to split it into, just every time you put Scotch tape on two sides and split it, you make it twice thinner, and then if you do it many times, you basically get into exactly single layer. To our shame, we still use the same method, and pretty much every single research labs, we all use this method up to now. Because it takes like 2 minutes and you get the highest quality material immediately. But of course, it's not good for applications. Luckily, these days we've got, depending on the price you want to pay, on the quality you want to achieve, we've got like many other ways how to produce graphene. Say for electronic grade graphene, say for optoelectronics, for transistors, there are transparent interconnects and so on. You would use the so-called chemical vapor deposition. So what you do, you take carbon-containing gas, like methane, for example, and you run it on top of a hot catalytic surface. Usually copper is used, but you can use some other metals as well. And this gas, it cracks on the surface, and hydrogen then flies away, and carbon rearranges itself on the surface. And so it's a standard technique. So there are many companies, Sony, Samsung, they all got those large fabs how to produce this material by this method. And the beauty of the method is that it's pretty much agnostic to what kind of carbon source do you use. For example, a few years ago, we needed to make iron-doped graphene. So what we've done, we use this. You basically prick your finger, spread it on copper, just stick it into the furnace, and then voila, you get your iron-doped graphene. It was again meant as a joke. So, but my students got a bit of a twisted sense of humor. So I mean, it's cheap for them, so those fingers are mine, and then the blood is mine. So, but they actually pushed it a bit further, and we even published it as a research paper at the end. But of course, every joke got a bit of a joke in it, and I'm sure that you've seen pictures like this everywhere in the world, that we burn the supporting gas on every petrochemical or refinery plant. It's even worse at the oil wells, but because we burn a lot of supporting gas there, because we cannot. It's just not economical to transport it, and methane is much worse greenhouse gas than CO2. It's better to emit CO2 than methane, but in those flares, we've got everything what we need to produce graphene. So we have the high temperature, we have the carbon-containing gas. So we basically develop those machines which can turn this methane into functional carbon. And it's becoming even more relevant because lots of companies, especially in the countries which are rich in oil, they look into the opportunity how to convert, how to burn oil without emitting CO2, and they basically create gray hydrogen by cracking oil or carbon-containing gas into hydrogen and carbon. And for them, it's really important to make this carbon functional, otherwise they lose about 30% of their revenue. So when you burn your hydrocarbons, 70% comes from burning hydrogen, 30% comes from burning carbon. So, and it's really, for them, it's important that we produce functional carbon. So we work a lot now these days with Aramco, with Sinopec to develop methods to produce functional carbon during the production of gray hydrogen. And that actually works, and we can produce indeed quite a lot of either carbon nanotubes or graphene. It works fantastically well. The only problem is who needs that much graphene? Because we produce trillions of tons of hydrogen every year. No one needs trillions of tons of graphene. Just for you to realize how thin is this material, one of the applications for graphene is in touch panels in your phones. Now, if you replace all the touch panels in your mobile phones in the world, you would need 1 kilogram of graphene per year. It's just because it's so thin and so light. So what are we going to do with the other 999 billion tons? I don't know. But luckily, there are actually applications which can take large amount of graphene, and that's in construction industry. It's actually one of the projects on this is here in Italy. And so it turns out that if you add a minute amount of graphene into concrete, like 0.1%, you can improve the compressive strength of concrete by 30–50%. So you add a little bit of graphene there, and you need 30% less of concrete to build buildings of the same strength. And of course, concrete industry is one of the largest CO2 emitter in the world. So what we do, we take carbon from the atmosphere, we put it into concrete, and we reduce the carbon emission even further. So it's really a fantastic example of the spiral economy. Well, even better, so it works with many other concrete structures. So there is this, the new type of concrete is the fibrous concrete, where you use not the steel rebar, but either glass fiber or mineral fiber for the reinforcement. It works really fantastically well, much easy to deposit. You don't need to put the rebars. The problem is those fibers, they corrode. They don't like the high pH environment in the concrete. So what we do, we coat those fibers with graphene, and then we stop the corrosion. So the expected lifetime becomes at least five times longer than if you don't coat it with graphene. And then, because we can put quite a lot of graphene and quite a lot of this fiber, your concrete starts to be conductive, and so it's really good for example, crack monitoring, failure monitoring. So because you can simply measure the resistivity of your concrete slab. It is sensitive to internal cracks as well, so it's extremely good for monitoring the failure. And even more interesting, because we can make it conductive, we can turn our concrete slab into a battery. So those so what you see on the picture, so the middle part is the concrete slab. So we just in our labs, we are lazy. We don't like carrying big slabs of concrete, so we just make small devices out of it. But essentially, it's just normal concrete, and we basically turn it into a battery. So now you don't need to buy batteries from I don't know, CATL or BYD. You just cast the slab in your house or in the walls of your house, and you turn those into battery. So it works really, really well. So I think one of the biggest application is for the solar farms or for wind turbine. You always need ways how to store a large amount of electricity there, and though you just cast your foundation, your slab, and then it works. So and then there are many other ways how to produce graphene, but then the next part of the story happened when, well, we've been working on the graphene for some time. And then at a certain moment, so we started on a shoestring, really, just literally with the pencils. When some funding started to appear in our lab, we could afford to buy not only the lead pencils, some other pencils as well. And it turned out to be that if you exfoliate other pencils, we can create other two-dimensional materials. So these days, we're talking about not just graphene, but we talk about a whole family of two-dimensional materials. They're all only 1 atom thick, but they would have very different properties, from being most insulating to the most conductive to semiconductive, ferromagnets, ferroelectric, superconductors, so you name it. And it's really a beauty, because you can study physics in 2 dimensions for many different applications, but it also gives quite an interesting opportunity. And let me just give you, step back a little bit and give you a little bit of the history lecture here. So materials are quite important in humanity, right? So we even call the ages we live in by the names of the dominant materials. So we've had the Stone Age, the Bronze Age, the Iron Age. Chinese add also the Porcelain Age. But it's a good question, which age do we live in now? And surprisingly, well, we live in quite interesting time, because there are several technologies which dominant. So you can call it the Silicon Age, maybe the Nuclear Age, or the Digital Age. Or just maybe, so we have a choice, but maybe it would be good not to make this choice, not to really choose the dominant material at all, because it, of course, brings some benefits if you have one material which you know inside out, but it also brings some problems. Let me just give you one example here. So this is the periodic table of elements which we use in our silicon technology from the very beginning until 1990. So you basically have silicon, of course, then there is boron and phosphorus for doping, and then aluminum for interconnects, and hydrogen, oxygen for passivation. Very, very, very simple technology, but very efficient at the same time. So that's the reason why it has been developing very, very fast since 60s. Then after 1990, we needed better integration. Our transistors became smaller. Aluminum is not the best conductor, so it would overheat your chip, so we switched to copper. It all immediately bring other problems, so it start to diffuse. You need the diffusion barrier, you need work function matching material, so you add copper, and then you had to add quite a few other elements as well. So you increase the complexity of the technology, but still manageable. So these days, we actually use more than half of the periodic table in our silicon technology. And the reason for that is we basically started with material which really bring you efficiency and simplicity, and because you didn't have the guts to switch to something different, all the investments are there in silicon. We kept improving this technology, and we kept modifying this, but the complexity increased beyond belief. So it's instructive to compare the the elements which we've got in our body with the elements which we use in silicon technology. So it's actually, our body looks like much simpler than our silicon technology, and yet, of course, we are much more versatile than our chips. So, and that's true with many other materials as well. So there are only few materials which determine our world. It's like electronics, it's silicon, construction engineering relies on concrete and steel. The airspace is aluminum, titanium. So basically, we are slaves of those few materials. And ideally, you don't want this. Ideally, you want the freedom of designing new applications without thinking which materials have we got. So for that, it's humanity, we thought about the composite materials and the heterostructures where you mix different materials together to achieve new properties, but those examples are still few and far between. So ideally what you want to be able for each new application to build a new material from scratch by atom, or maybe layer by layer engineering, because then you can assign certain functions to each of the layers. So my top layer is some solar panel, for example, which gives me power. The next one is the logic and so on. And with the advance of the 2D materials, we actually have this opportunity, because I come to the lab and I have, in my lab, I have the selections of those 1 atom thick crystals, which each having different properties. And what I can do now, I can build them into a 3-dimensional stack, into a heterostructure with atomic precision. That's exactly what our students do every day. So they, unfortunately by hand, so they put one layer of one material, another of another, and just build those artificial materials which don't exist in nature. And we build it with atomic precision, and we can really build them into new materials which also are functional. So the difference between device and material now disappear. Your whole stack become functional, become a device. So we build new type of transistors, new types of solar cells, photovoltaic LEDs, resonant tunneling transistors, and so on and so on and so on. And just to finish on this, to show you what kind of flexibility we've got, it's not only which material do you stack together, but also how do you stack them together. Imagine I can take 2 layers of graphene, but also I can rotate them slightly with respect to each other. And I hope you can see there's mesmerizing pattern appearing on the screen. It's called the Moira pattern. And this Moira pattern actually gives you additional potential, additional scattering for your electrons. You control the band structure, the electronic band structure, and through this way, we can turn our graphene into a superconductor. So you just take 2 layers of graphene, which are quite bad metal, and bad metals are usually not good superconductors, and you twist them a little bit, and you basically make it into a superconductor. If you take 2 + 1 layers, you can make it into a ferromagnet. So really, the flexibility and the opportunities which we've got with this kind of material engineering are really endless. So basically, you can see that we really have a lot of opportunities here. And so this is really the dream of material science, because you basically have got just you tell me what kind of properties do you want to achieve from your material, and I can construct the material for you with the atomic precision. So that looks like the end of material science. So we started to think, what's next? What kind of materials, what kind of new challenges can we achieve? And rather than answering this question by myself, let me show you how other people answered this before. So I'm sure that all the people in the audience would recognize this movie. It's Terminator 2. For younger people, it's the movie from my childhood. Was made in 1991, And the plot of the movie that a robot from 2029 sent back to 1991 to kill Sarah Connor and her son. And the only reason I'm showing it to you is to show how people back in 91 thought our future robots would be. So just made from liquid metal, being able to change shape, change in color, adapt to environment, so self-healing, and so on and so on and so on. So we are in 2026. And I've got bad news for you that unless we do something drastically different, we don't have any chance to fulfill the dreams of the director of Terminator 2. And the problem is not just with the robotics. The problem is fundamentally with our technology, which is has this so-called top-down functionality. So the individual components in our technologies are not functional. The functionality and the complexity appears only on the system level. So you take one cogwheel from this clock and it stopped working. So same with your integrated circuits, you take one cogwheel from the one transistors out of this and it stopped working. So biological systems instead, they work on a completely different pretense. So there the functionality is spread across all the possible levels. Individual proteins are functional, membranes of the cells, the organs, and so on. So each have got their own functionality. Where I can take, say, a membrane from the cell, and I can use the ionic pumps from that membrane outside of your cells. You can't do this with so the functionality is still there. And that's what we were trying to change. We were trying to create functional, intelligent materials. You don't need to read this. Let me explain just give you one example to demonstrate what do we mean. So one of the applications for graphene is in water desalination, and membrane technology for desalination become more and more important. In Singapore, where I'm now, 99% of our water goes through the membrane. So it works nicely, but of course you still have to monitor the quality of water which you produce. You have to put a sensor downstream which sends a signal to the computer, which analyzes the signal. If there is anything funny there, it sends a signal to the actuator to close the valve. Now imagine that in this membrane I can put some signaling molecules which could be sensitive and to the presence of certain toxic species. So then once they're there, so it changes those molecules would change the conformation and would open or close the pores. So now my membrane itself is a sensor, is a computer, and is an actuator. It can make a decision, and you can even train it to make a decision if you need. So now the material itself become the active part of your your technology. So I should say that it's actually we know how to make it. We're trying to figure out the fundamental principles behind it. I won't go into details, just to say that we are trying to make it in a similar manner how proteins in your body work. So proteins work, and proteins are so versatile because they can exist in multiple conformations. They go through phase transitions and they put out certain functional groups so they can catalyze a different reaction. So we're trying to make our artificial materials to work in a similar manner. They can go through different phase transitions and they would have different functionalities in different phases. The problem is that it's a very, very challenging task because in physics we simply don't have the apparatus to study this out of equilibrium phenomenon. Of course, this phase transitions is usually out of equilibrium. So what we do, we try to utilize the power of AI, and it's quite a specific, so we call it dynamic AI. But of course, any AI application require a lot of data, so we spent a lot of time on developing our robotic system to generate enough materials, enough data. And when I say about robotic systems, people think about something like this. We do have those, so we filmed our students, and so our colleagues reproduce this in the robotics. Personally, I still prefer the traditional methods. Those robots, they absolutely don't react if you shout them, "Hey, you idiot!" So it's very, very difficult to communicate. So typically, we have slightly different types, so more robust, more well-programmed systems, so which can make simpler tasks, but very, very robustly and very reproducibly. So these days we're working on our automated lab 3.0, so where we combine the modular system, so something in between, so to gain both the flexibility and the precision. And of course, so we produce a lot of databases with those materials. The problem is that unfortunately, when it comes to the creation of the materials, usually those databases, they don't really work. So we apply a lot of efforts to make the databases, to train our AI. It's all available online and nice platforms. And then you try to simulate the behavior of actually our very good, catalysts, and they actually work, but the theory AI predicts that they shouldn't work. And it's really, so there is a huge challenge there. So I won't go into details, just to tell you that we are not the only idiots who really fail miserably here. Here is the example of the famous paper from Google DeepMind from 2.5 years ago. So they analyzed more than 2 million new materials. They came with the conclusion that about 400,000, almost 400,000 of those are stable. They tried to synthesize 58, managed to synthesize 43, and none of them actually turned out to be new. So, which tells us that, I mean, and again, this is really nice and beautiful piece of work. It just doesn't work, and it's I mean, there are many other examples like this which I can get. And the reason for that is that when we think about materials, we think in a very simple manner. We say iron, I don't know, rebar, or silicon transistors. So we put this data on silicon and on iron into our databases. But in fact, we forget that with the materials which we use, they're dramatically more complex than that. So we don't use pure iron. We use alloys. So alloys, you add a little bit of carbon, a little of chromium, I don't know, magnesium, so zirconium, just something there, and which makes the unit cell huge, so we simply cannot compute that. Even worse, the unique properties of iron, the plasticity of iron is not coming from its chemical structure. It's coming from its morphology, because it has the unique grain structure and then unique combination of different phases. So maybe face-centered or body-centered and so on. And then we also make nanostructures out of it, which is an additional level of complexity. Exactly the same with silicon. We don't use pure silicon. We dope it, we create PN junctions out of it, we create transistors, nanostructures, and so on. And that all is not captured, unfortunately, at this moment. So but, I mean, we need to apply so much more efforts, because, of course, ChatGPT being trained on a huge amount of literature. So for materials, we only use few thousands of those examples. So we really need much more realistic examples to put in. So what we do these days, we basically, rather than creating this connection between the chemical formula, chemical composition, and the properties, we work on the synthesis level. We look how synthesis is being performed, and we really look closely inside of the reactor, and then we create this database of the chemical reactions, and then we can put it into the training for our AI, and then hopefully we can design new materials. So we started on AI for materials about maybe 5 years ago. We made the usual steps, what everyone does. So a couple of years ago, we changed the direction. It's much more challenging, but unfortunately, I don't think there is an easy way around it. But it's also good fun, both on the experiment side and on the AI side. So just maybe I'll give you one example. I won't go much into details, but to give you one example, how do we simulate dynamic materials? Because I told you that we're not interested in simple materials. We can understand their properties even without AI. What AI really is required when we need some dynamic structures, like proteins, for example, so which can fold and unfold. And you know, the ground state, the most low energy state, is being solved by alpha folds, so for which were awarded the Nobel Prize. So our task is more challenging. We're trying to design all the metastable states. So, and for that, we basically learn on the dynamic properties. We look at those proteins, how they stretch, unstretch, and we put all this information into our AI, and we learn this. So essentially, every time we look at this, we create the new type of physics, because we reduce the dimensionality. So a good example is to remind you how thermodynamics works. So thermodynamics, you know, you use it usually to describe the behavior of liquids, maybe of gases. So if you want to describe the behavior of gas molecules in this room, the most straightforward way is to write Newton equation for each of those molecules, solve them, then you have the billions of the equations. If you manage to solve them, then you know everything about the gas in this room. However, it's of course not practical, if possible at all. So as humanity, we invented an alternative method, which is called the thermodynamics. We just noticed that there are a few parameters, macroscopic parameters like pressure and temperature, which are connected, and they are enough to describe the behavior of gas in any container. And it's really a beautiful approach. The only problem is, how do you guess that you need to have exactly those parameters? I mean, temperature for us now is, of course, it's an easy concept, but you should just, if you remember that it took 200 years for humanity to develop the concept of temperatures from Celsius to until Planck, basically. So 200 years we needed to understand the meaning of this temperature. But now we're trying to do it for any other complex system. So we ask AI, look at the dynamics, look at the gas molecules, or look at the dynamics of the proteins, and give us the equation which actually describe this behavior. The equation is unfortunately not written, so the equation is in the form of AI matrices, but that's exactly what we mean. Again, I won't be bothering you with all the equations. Just the answer is that we actually can predict. So the behavior of so now our computers, they look at the structure of the protein, and they can predict precisely that if you stretch it, it will be very difficult, or it will be stretched straight away, because we can produce a simplified description for those systems. And now we are applying it for more practical. I mean, proteins are important, but there are some other things like complex alloys, for example, high entropy alloys. how to assign them new properties or complex magnetic structures as well. And let me just show you, before I finish, show you a few examples of the successful examples how we managed to produce those dynamic systems already. So one is the high entropy alloy. High entropy means that you mix many different elements there. So usually you have like alloys like cast iron is basically iron plus carbon. And so in those alloys, we have maybe 7 different metals plus oxygen all mixed together. But if you do it right, you can actually assign some very unique properties to those. So what you see here is the microscopy picture. So in the tiny dots everywhere are the individual atoms. And what we did, we drilled a hole through this. So there is a hole in the middle. And if you design it right, so then this alloy, this hole will gradually disappear. So we really assign new properties called the self-healing. It's almost biological properties. Like when you cut your skin, it will regrow, regenerate after a while. Same with those materials. We store enough energy, and we can direct this energy into a particular task, so that if you make a scratch on your car or you drill a hole, it will regrow itself completely. So another example is the smart drug delivery. So we all had to take COVID-19 jabs and you cannot take it orally because those active molecules, those mRNAs, they're very unstable in the lower pH, higher acidity of your stomach. So if you want to do it orally, you would have to wrap it into something protective, and then it would go through your stomach and open up only in the intestine. And that's exactly what we produce. We make those nanocapsules which can be programmed to stay closed in your stomach and then open and release your drug when it is already in the bloodstream or in the intestine. I can't show you the microscopy pictures. Those are really tiny nanocapsules, but they work. So we are testing them in vivo now. But we can make macroscopic examples of those. So we make materials which are active, which act as basically as machines by themselves, and so basically you can program them to be sensitive, to be reactive for light or temperature or pH, humidity, you name it. So that's. The better AI models we create, the more higher precision we can develop those materials, the more complex behavior and the more complex interaction with the environment. And before I finish, let me just show you another track. So up to now, I was showing you what AI can do for materials, but as Fabio mentioned before, we also try to follow a different track as well, what materials can do for AI as well. And of course, you know that it's becoming a serious problem these days. For years, the sustainable electronic industry been assured for us by 2 laws, by the Moore's law and by the Dennard's law. Moore's law would tell you that the number of transistors on your chip increases by a factor of 2 every 18 months. And the Dennard's law would guarantee that even though you have twice number of transistors, the power consumption won't increase. So that was the reason that our growth, the growth of electronic industry was sustainable for many years. Unfortunately, over the last few years, this Dennard's law started to fail. We face so our chips start to overheat dramatically. So the heat dissipation with graphene is now really is a huge business. NVIDIA puts a lot of graphene into their chips. But we're really facing this power wall that we need to do something about this. And we have those new directions, new opportunities. There is quantum computing, there is neuromorphic computing, but there is also probabilistic computing. So in our lab, we work a little bit on quantum, but in reality, it will still take quite a few years before real quantum computers are going to appear. So we, as the interim solution, we work a lot on the probabilistic computing. And just let me explain you what it is. So in classical compute, your electrons is the carrier for information, and they basically work independently, one by one. You just either send electron, which is bit 1, or not send electron, it's bit 0, and you just do your computation. You have to test every single path. In quantum, all those quantum bits, the qubits, they are interconnected and they evolve simultaneously at the same time, and that's why they can explore all the possible solutions at once, and they give you the one solution which is the optimum. The problem is that as the complexity of the system increases, the decoherence kills that, and it's very, very difficult to operate with those quantum computers in scale. So the alternative way we should have is the probabilistic computing. So we still got those quantum bits which can randomly be in either 1 or 0 state, but we entangle them not inside of the system. We entangle them outside through the computation in the classical computers. It's slower than quantum, but still much faster than the classical, because we indeed explore the whole space of opportunities at the same time, even though the entanglement is done through externally outside. And it's basically and it's really good for optimization problems. So like those protein optimization, it will be solved with the quantum or the probabilistic compute extremely fast. So optimization problem is that if you've got a very complex landscape, for example, you need to go by skis from the top of the mountain to the valley, and there are many possible routes, and you need to figure out which routes do you take, which route would be the fastest. The classical, there is no any other way but to test every single possible route, and then after you tested all of them, you know the solution. In quantum and in the probabilistic, the system just anneals in such a way that it explores. Due to this quantum entanglement, it explores all the possible routes in one, and just as it settles down, it gives you the one solution. So it's really ideal for a number of different applications, and there are many different ways how to do it. So there is, in terms of the physical realization, but there are many ways how to do it, and it's really good for many different optimization problems, like from image generation to portfolio optimization to logistics. So we work with many logistic companies these days how to solve their optimization problems with our probabilistic compute. So I think I will stop here just to say that it's so already now we have this level of the material science when we can create new materials with atomic precision with the predetermined properties. But that's not enough. So the future is in functional materials which can think, which can adapt, which can do something functional. And so we're developing those as we speak. And it's really, and the AI will be one of the most important tools for that development. So thank you so much for your attention, for coming here, and it's really a great pleasure to be here in Turin. So this morning we found lots of opportunities to collaborate, so hope to come here again. Thank you.
So, thank you, Kostya. First of all, I want to mention that he didn't use a pencil only to produce graphene, but he's also an artist, and he gave me one of his artworks, so an excellent artist. And then I also want to mention that those robots that were playing football are simply Fiorentina players, so don't worry, but we are improving. So now, I leave the floor to questions. There is anyone who wants to raise questions for Kostya? I leave. We cannot see you, so you should take the lead and.
Just shout if you got any.
We also have the microphone if needed. Yeah. Ooh, sorry.
So thank you very much for the talk. Very interesting and stimulating. So it's very well known, for instance, in vision, that the data sets composed by images are not enough to produce effective AI systems. I mean, if you really want to reach performance that are, say, superhuman in vision, you need to do what is called data augmentation. And this data augmentation is based on the understanding of properties of images, like, say, you perform certain rotations, some elastic deformation, and so on. So it seems to me that material should be a good playground for this, in the sense that you have a lot, I mean, you could imagine how to augment the data based on your physical understanding of systems. So that would be the objective in order to have effective systems.
Right. So that's part of the thing which that's part of the problem which we're working on. But materials are a little bit more complex than images. So images it's more or less continuous. It's the continuous space. Crystals, materials, they really follow certain rules. So you can't move an atom in a crystal arbitrarily. So they are really fixed, and there are certain rules there. And that's why that's why the space, when you do the transformer, so the latent space is extremely sparse. So it's very, very difficult to group and to navigate and to design metrics in the latent space. So we have to explicitly put certain properties into it, the symmetry of the crystals, some of the chemistry, and that's not easy, because one thing you want to be continuous, so to generate new crystals, you do the standard diffusion or whatever, but at the same time the robust limitations are there. So and how to combine the two is not easy. So that's but I'm sure that it will be done. It will be solved on the mathematics side. But there is another problem. There is physical problem, which, I mean, I'm an experimental physicist, so I'm much more excited about those problems. That anything what we predict, that it's really good for, so that it's the fundamental property of those materials, but it doesn't guarantee the synthesizability. That you found something stable doesn't guarantee that you can actually get into this through the synthesis. So that's so how to create what AI predicted is another big question. So yes, I agree that there is a question about the latent space and how to create the best description for the latent space to generate new materials. But there are many other problems as well.
Thank you, sir, for your nice presentation. So I have only my curiosity. Since you are an experimental physicist, as you said about high entropy alloy, let us assume we have used AI to model a new high entropy alloy, and it come out like some output of this alloy will be coming out. But how can we ensure the stability of that alloy? So as an experimentalist, should we use classical methods for material design, for the alloy design, or should we try for this AI? I am asking, like, should I enter into the race of AI, or should I stay with the classical method?
I mean, AI can be, so it's agnostic to quantum mechanics or classical. Personally, I don't really like this story about entering the race. So it's not a race, and believe me, you will see that many ideas will fail and will get us into the wrong direction. I mean, what I presented to you is what we're working on now, and it's quite possible that 50% of these are going to be abandoned in a year or two, because there are other better solutions. So it feels like a race, but in fact, I don't think we need to be bothered. Quantum or classical or AI, I mean, I don't think about it this way. So those are different tools which we use in our everyday scientific life. So what do you use? The quantum mechanics or molecular dynamics or thermodynamics? It really depends on what kind of problem are you trying to solve. So I believe that the complexity which we've got now of the materials which we're trying to design, of the structures, biological structures we're trying to design, is such that we need the help of the power of AI. But at the end of the day, it's all physics, and we would need to put some comprehension into it as well. I don't believe in AI without understanding. So in that respect, classical or quantum understanding will have to be there anyway.
Thank you.
Thank you for the wonderful talk, Professor. I have a fun question and a serious question. So the date I saw in the PPT is 18th March. So did you travel to the future? And the second question is on the TEM images. I wanted to understand, how are you planning to implement the AI in advancing TEM analysis as well? Thank you.
Yeah, sorry, it's automated date, so it shows my jet lag. So I'm working on Singapore time. Sorry, can you repeat the second question, please?
Yeah, I wanted to understand more on the TEM analysis and how AI are you planning to implement it for advancing that?
TEM. Yeah. You mean the last high entropy alloy with the self-healing, or?
The transmission electron microscopy analysis.
Yeah, the only TEM I showed to you was with the high entropy alloy with the hole, and then how it closes. I mean, I can try to give you the hand-waving explanation how it works. Basically, when we create the high entropy alloys, we freeze it, we quench it in such a way that different elements are sitting next to each other. And in reality, they don't really like to sit next to each other. They want to group with their own kind. But because at high temperature, they're strongly mixed. So when we quench them, they're fixed there. And ideally, they want to jump and rearrange, but in the crystal structure, they cannot. Now, when we drill a hole, we create an empty space, and then this energy of the interaction, which they have because they are pushing each other, so this energy start to be released into restructuring them. But then, of course, this restructuring can go both ways. This hole can increase or it can decrease, and what actually makes it to regrow, I don't really know. I know the source of energy, this entropy, so the entropy is the source, and we understand where it goes, it comes from, but that's about it. So the details, why it actually regrows and it regrows in a particular state, I don't really know. But just let me explain you maybe a little bit better my motivation in studying those. So I mean, it's nice to have these self-healing materials. It's cool and so on, but that's not our motivation. So for any physicist, there are at least two problems which we always just swipe out under the carpet. So one is the problem of thermodynamics. So we have this Newton's law, everything predictable. So if you write an equation, so it can go back and forth in time and so on. So, and then there is thermodynamics, which tells you, oh no, so the everything is developing only in such a way that the entropy increases. And you really don't understand. So if you, so like those poor students who studied like for 3 semesters in the university, so they know classical mechanics, they know molecular dynamics, they come into the thermodynamics, and they don't understand why these two fields of physics are completely disconnected. So there are ways how to, many people try to connect it, but it's not, but there is no good explanation behind. And then the second revelation comes when we look at the biological systems, and there this thermodynamics doesn't work again. So there the entropy, which is supposed to increase, so we all should rot, and then and we don't. So we manage to rectify entropy. We manage to increase order rather than decrease order. When we die, the order, so the disorder prevails, so we decrease, we all rot. So that's when the entropy goes up. But while we're alive, for some reason, entropy, we've managed to control entropy at least locally and temporarily. We've spent a lot of energy on this, but we still managed to do it. And that's something which is really puzzling for physicists. How can we break this second law of thermodynamics? So those are the examples of systems, complex systems, which at least temporarily and locally break the second law of thermodynamics. So that's the biggest motivation for us. We try to create systems which behave in a biological manner, at least on certain scale, and we hope that that would be a pathway to understand the biological systems, or to understand life.
Hello.
Yeah.
There was a nice, interesting presentation. I got multiple sclerosis, and I got dysentery, so be patient. You showed a slide that demonstrates material turning on itself because of the red light. I would like to understand more that thing.
Right. I mean, so we have some vague understanding of the forces behind. So for the drug delivery, for example, it's reasonably simple. So we don't need even AI for that. But for more complex machinery, which when we create, so it's really, at the moment, unfortunately, it's more trial and error, and you create some mental model, you try it in experiment, it doesn't work, you change your model again. And so there are some explanations, some hand-waving arguments. We can probably improve it better, but it's still a lot of trial and error at the moment. I wish I could be more positive in that, but at this moment it's extremely, extremely experimental. So I'm just showing you what things which happened in the lab over the last 18 months. So it's a lot of experiments. So it will take time before it will go into the real applications, unfortunately.
Thank you.
We have many.
Thank you, and thank you for your presentation. You showed us some very interesting use of the AI to develop very complex materials. But nowadays, one of the biggest challenge is actually to have access to some key raw materials that can be denied one day from another, given to the war situation of the moment nowadays. Do you think that some of the techniques that you showed us from AI, using AI from thermodynamics modeling, can help actually to synthesize or substitute some of these key raw materials, can be used also for very simple materials rather than very complex materials?
Right. Unfortunately, we don't do alchemistry, and we don't do nuclear physics, so we can't synthesize, I mean, not in my lab, sorry, we can't synthesize new materials. But the hope is, of course, that we create new platforms and we will replace those materials with the new ones. Say, silicon technology has been there for forever. The question is which material is coming after silicon. So these days, most of the semiconductor companies like TSMC, for example, they work on the future materials, and the best candidates which they found is one of the materials I showed to you, the two-dimensional MOS2. And of course, but if you change the technology, you would change the contacts, you change many other things. Whether we would need the same amount of rare earths for MOS2 technology as for silicon technology, I won't be able to tell you, but it definitely will change the whole paradigm, and it will definitely change the distribution of power, and so the whole technologies are going to change. In which direction, I don't know. It can be better, can be worse. Just maybe okay, thank you so much.
Thank you.
If we can put the presentation on the screen, because Fabio said that, of course, it wasn't a pencil, and it indeed wasn't. So when we produced our first graphene, it wasn't a really pencil. So we used high-quality graphite. So at that time, and it's HOPG, and then switched to the natural graphite. And then years later, this lady, so she's a famous artist, Cornelia Parker, in London. So she's known for her shed which is in. It's a shed in Tate. So she came to me and said, let's do some show together. So what can we do from? And I paint a little bit, so she knows me for that. So let's do something. So we ended up so we decided to make graphene out of real pencil. But real pencil for an artist is boring. So what we've done graphene from the first pencil. So the first pencils were made quite close to Manchester, where I used to work during that time in the Lake District. That's the first graphitic mines, and so we took images, we took drawings from all the famous painters, Gertin, Constable, Turner. And I removed the unnecessary pieces of graphite from those pencils, just from those pencil drawings, just corrected those a little bit, making it nicer. And from that graphite, we made some graphene And so you actually, so the answer is yes, you can use the real pencil to make graphene. So we'll also use Picasso as well. So and then we just turned it into the real devices. So you can use pencil actually for graphene. Right. Thank you.
Before we wrap up the evening, I just wanted to say a few thank yous. Thank you, Professor, for this amazing lecture. Thank you, everyone in the audience, for participating. Thank you, Fondazione, for making this possible. And we hope to see you soon again. We are going to have our lecture magistralis at the end of the month. So keep an eye on our website, and have a wonderful evening, everyone. Thank you.